let's have a look at our current getAuthor method. I don't know what you think about this, but there's an awful lot of code and logic in here. That means that there's an awful lot of responsibility for one action. It's not always easy to avoid, so sometimes you might end up with actions or methods with more responsibilities than one, but if possible, staying as close to the single responsibility principle as is feasible is the way to go. Thanks to the action constraint we just created, we can vastly improve on this for our getAuthor action. Instead of having to write all this code inside of the getAuthor action that deals with deciding what to do depending on the accept header, we can use our action constraint to constrain a request with a certain accept header value to a specific action. So we're going to split this getAuthor action up. We've got 4 potential results here, all depending on the accept header. We've got a regular author, that's the friendly version with a concatenated name and an age field. We've got a regular author with HTOS links. We've got a full author, so that's the one with first name, last name, and date of birth fields. And we've got a full author with HTOS links. Thanks to our new constraint, we can now nicely split this up in 4 different small actions. So let's do that. Let's start with the first one. This is our default version, getAuthor without links. It is routed to an application JSON, or our custom media type describing a friendly author is passed through as an accept header value. We first include the data shaping check. We try to get the author from the repository and check whether it's found or not. We map it to a friendly author, shape it, and return it. On to the second action. This is the getAuthor with links action. It is routed to when HTOS links in general are requested, or the friendly author with HTOS links is requested. It contains likewise code as our previous action, with one difference: we are now adding the links. 2 more to go. getFullAuthor without links is the action that is routed to when a full author representation without HTOS links is requested. Again, likewise code as we previously had, but we're mapping to an author full DTO here. And finally, we've got the action that's routed to when the full author with HTOS links representation is requested. It's the same as the previous action, with one difference: the links are added. And that's it for our 4 actions. We can now get rid of this old getAuthor action here. I'm going to leave it in the code, but comment it out so you still have it for reference. Anyway, this already looks a lot cleaner, doesn't it? Let's give this a try. I'm not going to run through all these requests again, but let's say we're going to try and get a full author with links just to test. And there we go. That indeed seems to route to the correct action and return the requested result. So far for that. We can go one step beyond this, because media types for input and output can be combined. You could now enable a consumer to create an author and then request one in friendly format in the response, or as the full type. We're not going to implement that, it's just a combination of what we've already done in this module. So if you want to do that, you know how. We do need to talk about one more thing, and media types come into play here as well: versioning. When we talk about versioning, we're actually talking about adapting to change. An API changes in different ways. What we can do with the API changes: we may be allowed to create an author today, but we might not be tomorrow. Or resources might be added or removed. Those are functional changes. Related are changes in business rules, like in our example in the previous module. The minimum age to make a reservation might change. And then there's changes in resource representations. Sometimes fields are added or removed. We need to be able to adapt to this without breaking consumers of the API. Adapting to change like this is evolvability, and that is one of the key concepts we've been talking about throughout this course. A versioning strategy is one way to do that. There's different things you could do. You could version the URI. You could pass through a version via query string parameters. Or you could use a custom versioning header. But is this a good idea? Let me quote Roy Fielding once again. In August of 2013, he delivered a keynote talk at the Adobe Evolve conference, where he was asked how we should version RESTful APIs. His answer was, don't. I read that and I thought, well, this does not make sense. One of the principal rules when building APIs is always version the API. Stuff changes. We should be able to adapt to it. He added to this don't statement by asking the question, when was the last time you saw a version number on a website? Keeping in mind that REST evokes the image of a well-designed web app, he makes a great point. But there's a bit of an issue with this at the moment. How do you adapt to change in a RESTful world then? Well, change, which is what we actually want to control when talking about versioning, comes in those flavors we saw on one of the previous slides. And we know how to tackle this. If functionality changes, the HOS links take care of it. If business rules change, same story. The applications that consume the API must look at these, and if they do, they will not break if one of these changes. But what if resource representations change? Fields can be removed or added, for example. Well, that's still a problem. According to Mr. Fielding, these should not be versioned either. But to allow for something like that, we're back to our initial problem. How can we let consumers of the API know what the representation should look like? And moreover, how can we make sure these consuming applications automatically evolve when the representation evolves? The option to fix this, according to Mr. Fielding, is the code on demand constraint. That is the optional constraint that stated that the API can extend client functionality. A good fit for JavaScript-based applications. The consuming application downloads the JavaScript and it's thus up to the API to change this JavaScript when resource representations change. The JavaScript could then contain object definitions for each of these media types. From that moment on, we would be truly evolvable. But that's JavaScript. It's a different story when you need to support different types of clients built in different languages for public RESTful APIs, some we might not even know about. Moreover, all these types of applications will almost have to be auto-generated. An additional field would mean an additional text box in the UI. So, if the resource changes, well, the UI should adapt. And that is much like how a web application works, and after all, REST was conceived with the image of a well-designed web app in mind. The browser gets back a response from the server, interprets it, and shows us the web page. It fully generates the user interface from the representation by interpreting HTML, JavaScript, CSS, and the likes. So, what Mr. Fielding states makes sense. But more often than not, our client applications don't self-generate. What we build is, well, not ready for that yet. So it's a great idea and it leads to true evolvability. But currently it's not feasible for the majority of applications we build. So for this specific part, I prefer to divert a bit from the best practice Mr. Fielding suggests, but of course still adhering to the RESTful constraints. What do we do then? Well, for resource representation changes, we can use versioning on that level. It's a new type of representation, so we create a new media type. We thus version representations through media types. You could do that with friendly names like we did, or you could do that by adding version numbers to the media type. To ensure that client apps don't break, we support both versions, of course. So, version 1 can still be used by existing applications, and version 2 can be used when these applications are changed. It's still according to the REST constraints, so we're good to go. With that, it's time for the summary. The last two modules were focused on HateOS and media types. Correct use of these often separates APIs that intend to be RESTful from truly RESTful APIs. But in reality, what we really learned about was evolvability. These were also the modules in which we learned that building a RESTful system is a lot different from building a standard web API. As we learned, a custom media type should be used when a consumer wants to include these HateOS links in the response body, as it's a different representation of the resource. These media types are a key principle when building RESTful APIs. What we did up until this module, using application JSON for our resource representations, actually isn't completely correct. An authored representation with first name, last name, and date of birth is different from a representation with name and age. These are different media types. We shouldn't use application JSON for that. Instead, we should create separate media types for these. By doing so, we're attaching semantics, in other words, meaning, to what a client can request or input. And that leads to better evolvability and reliability. That then led us to adapting to change and versioning. We learned that we should use HateOS for changes to functionality and business rules, and that until the code on demand constraint is feasible, we should choose versioned media types. Building a truly RESTful API does take a bit of work, but the evolvability it was designed for is worth it. And we're talking systems that are built to adapt to change over years or even decades, not months. That's it for HateOS and media types. If used correctly, it can be a tremendous addition to any API. One more constraint remains, the cacheable constraint, another big one. We will look into it in the next few modules.